Good. So I will introduce you then.
Sure, thanks.
Yes. So we had a few problems with the hybrid equipment. Usually always works, but now we have like multiple versions of the hybrid. So my lab is connected via Sophia Simon right there. Hopefully anytime we are going to have more visibility to the hybrid. So my lab is has like around 10 people, and they later can introduce themselves to you. But for now, I will let you introduce yourself to my lab, and then we will do the opposite probably at the end of the talk.
Yeah, okay. So how long do I have?
You have until, you have an hour and 20 minutes.
Okay, all inclusive. Yeah.
All inclusive. And remember that we have another
session next week. Yeah. Okay.
Exactly.
So I'll start now. Well, first, thank you, Fernanda, for giving us the chance to be connected at this seminar. To me, it's an honor to be talking to your group, actually. I will introduce myself, but first I want to tell your students that I met Fernanda when I was her teacher assistant at the University of Chile. And I'm glad to know that my first impression of her has been right. I thought she is really great. She's gonna do a great job, and she's doing a great job. So it's amazing. She was a very brilliant student. So now is a brilliant professor. Great. Myself, I am Thomas Velos. I'm at this moment at the Technological Metropolitan University of Chile at the Biomathematics Group, Mathematical Biology. And I'm also affiliated at the Center Leo Apostel as a postdoctoral researcher. That's an interdisciplinary research center in Belgium at the Free University of Brussels. And I'm also the founder and director of a foundation for the interdisciplinary development of science, technology, and the arts in Chile, hosted in Chile. So I work as a professor, researcher, and sort of, we will say, social entrepreneur. So this is a little bit the activities that I move around. I can speak more about it maybe later, but today we will talk about a specific modeling framework. Actually, at this moment, we are in one of the courses that I teach at the Technological Metropolitan University. The course is called Stochastic Modeling. And on the other side of the screen, my students from the Masters in Mathematical Biology are attending to this seminar as well. So we got students on both sides. It's a very cool, modern 21st century experience. Okay, I go now to the outline of the seminar. So I will introduce to you a modeling framework that is inspired in chemistry. It's inspired in life, in the origins of life, I will say, but it's going to be applied as a general modeling framework for interdisciplinary science. So for science that is not easy to frame because it belongs to many different fields. And in specifics, it's going to be introduced as a modeling framework in ecology or social ecology as well. But in the second session, we will go over more details. Today, I will basically introduce the motivation, the framework, and a little bit of inspiration for ideas to think about how to apply this. So let's go. I will start with a very deep concept, which is at this moment that we have a grant for developing this modeling framework with the Templeton Foundation at the Free University of Brussels. We have a grant called The Origins of Goal-Directedness, and we are using this framework to explain what is goal-directedness. So why things go in the way they go, why we have consciousness and why we had life before, and why we have societies, or why there is a sort of complexification in the universe in terms of interactions and hierarchies and multi-hierarchies, let's say, that develop. As biologists, you probably understand very well what I'm talking about. But the problem is that this foundational question of what a goal is, it sorts of contradicts our current notion of what a goal is, especially in AI. So if you look at AI, what mostly is done is to think of a notion of that a goal is an optimization. When you have a goal, it's because you reach an optimal. The goal is an optimal that you have to, well, it's defined by functionals and so on. So if we look at this, this is underlying many theories, such as, for example, in evolution, we think that we tend to optimize some sort of fitness. In economics or decision-making, we tend to optimize our expected utility. In cell metabolism, in many models, they assume that the metabolism is optimizing some biomass production. And even in intelligence or consciousness, we tend to talk about intelligence or some intelligence-like concept as a optimization of representational features, predictive capacities, or problem-solving abilities. So we have like this idea of a complex landscape and somehow reaching the optimal is our God today, to think about how things go. And of course, this comes from the Hamiltonian, the least action principle in physics, and it's a very useful principle to explain many processes. But the problem is that goals, this question doesn't really explain how goals really emerge, how they configure in the first place. Once you have a system, of course, you can apply some sort of least action principle and go and arrive to some optimization process that will explain what is the underlying dynamics that is going to have. But the question is now, we think more in the complex system sense. So we have many entities probably having different behavioral rules or different interests. And then how can we even think of that optimal process in the first place? So this is the question. So how, for example, how life began? Is it that life began because something was becoming optimal, and then life was the optimal way to do something? So that's the typical question of the origins of life. Or is it that consciousness started as the optimal way of doing something that non-conscious beings were not optimal at doing? Or is it just another emergent feature? So the thing is that I will quickly claim that when there is emergence, the notion of emergence, like new rules dominating the game, then the optimization paradigm falls short. That's the basic idea that get us to have this grant, and that's a sort of first motivation to question the idea that pure optimization is God for science. We need something else, and that's called emergence, but we don't have a proper theory of emergence so far. So I will kind of speak about that. So now we got this complex and interdisciplinary world where we can see lots of disciplines or domains of understanding, such as, for example, we got cities, we got urban distribution, industry, we got cities, and we got money. And these three things kind of flow and co-develop in a sort of related way, but more complex than they just are related to each other. They are related in the context of what's going on in the other variable. So this is already questioning the fact that thinking in terms of pure arrows can be problematic, because other things can be the context for what's going on in the arrow. And also we got other issues such as the politics, well-being, biodiversity, and we somehow try to explain the world in an integrative way. So this is a very complex system because we have many perspectives, and the knowledge we have about the world is fragmented into perspectives, which are not necessarily complementary. They might even be conflicting. They might be contradictory sometimes. Doing right in one side is doing wrong in the other. So it's not always easy to think about these systems. And that's why when we have fragmented perspectives, which is generally the case in interdisciplinary science, we need to have an approach to represent the complexity of having these multiple potentially conflicting perspectives. So that's what motivates the study of complex systems. So I'm starting from the very beginning of this, so sorry for those that are experts in complex systems. What is a complex system in structural terms? Before thinking of disciplines and applications in general, let's just talk about the structural idea of a complex system. Many entities interacting in many and generally contextual ways. What are the salient features of a complex system? I summarize them in 4 features. Contextuality is the first, which means non-trivial dependencies between the entities that are interacting. This is exactly what I was mentioning in the beginning, that money and industry are not independent on what's going on in the city, in the urban planning, or in the city life, or in biodiversity. So everything can act as a context for the interaction of any pair of things. So there are non-trivial dependencies. And that what leads basically is to the idea of complexity, that things are sensitive, butterfly effect, non-linearities, etc. The second salient feature is feedback. That means that the output of an interaction can act as an input of that very interaction. So we will see the typical example of the Lotka-Volterra dynamics, and the effect is the regulation. Things tend to regulate because what they do affects what they will do afterwards. So there are feedback loops. Then when there are multiple feedbacks in a complex system, we tend to see self-organization, which is the co-regulation of the parts of the system through the coupling of the feedbacks. And then what we see is that there are stable wholes that emerge out of these multiple entities interacting in contextual ways. They develop some sort of feedback dynamics that ends up stabilizing or collapsing or reaching some sort of self-organized state. Nobody's telling them what to do, but what they do affects the other interactions in a way that everybody gets co-regulated with the system. So that's the effect, is the stable whole. And then the fact that you have self-organization that can happen in many different places, in many different at many different levels, creates that these wholes become entities themselves. So that's when you get emergence. If you have people living in the same, for example, in the same territory, they will use the resources, they will interact with each other, and they will form a society. And at some point, this little society, this little group, community, will be emergent and will have its own rules that actually regulate the way in which the parts act. So that's why we got social rules, social norms that don't belong to any of us, but we all respect and are part of the society. So we got an emergent layer, the society, that influence on the way in which we, the individuals forming the society, operate. And that happens in general in complex systems, in economics, in ecology, in whatever, urban planning, and all interdisciplinary sciences in general. Ecosystems are a perfect example to study this case, because you get, for example, the contextuality will be the available resources or the climate in the regulating or affecting, altering or changing the way species interact. Then the feedback, you can have examples like the prey-predator or the mutualistic interactions, where you see that the action of one affects the action of the other, which in turn affects the way in which the first one was operating, and so on. So feedback loops are very common in ecosystems. And then you get many examples of self-organization when you have adaptation to mutations or invasion of a species in a new place, in a specific territory. The inclusion, the arrival of a new species will modify all these feedback loops and will imply a self-organization, let's say, of the ecosystem. And then the emergence of ecological communities is the good example, that ecological communities in a specific territory work as stable wholes, and different places might have different ecological communities, and we can actually study the interaction between ecological communities not at the level of the species that form the ecological communities, but at the level of the communities themselves. So they really become whole, like entities at the higher level. Now, I will provide a quick criticism to the traditional ways in which we study complex systems to motivate the introduction of a new framework, which is the one I will introduce today. So the first one, I call it dynamical models. And here I define it as an analytic description of the interactions and dynamics by means of equations. Why do I say equations? Because they can be differential equations, as I show here, but they can also be discrete equations, like in the logistic map, for example, which is a discrete dynamics, or in the case of probabilistic equations, like a Markov chain or some sort of stochastic process defining the evolution, the dynamical evolution of a system. And the canonical example of this is the predator-prey system, where you see the feedback loops and the co-regulation of the populations of rabbits and foxes by these equations. And it is very famous. I don't say this is wrong, this is not bad, but the problem is that this can be properly analyzed. I mean, you can use the machinery of differential equations very nicely when you have small systems. When these systems become too large, the machinery of differential equations becomes not so useful because you cannot even integrate the equations. So it becomes like, okay, I cannot integrate the equation. Then I can maybe analyze the phase space in one way or another, but you start losing the framework becomes less and less powerful the more complex the system is. And then you start relying, we tend to rely on numerical simulations, which is still good, but it's not what we were aiming for in small systems. And the more problematic is that when novel entities and rules come into play in the system, then the equation changes. And we don't really have methods to deal with equations that change over time. As long as we integrate the equation and all of a sudden the equation changes, we need to start integrating a new equation on the basis of our final condition that we reached before the equation changed. And that is very, it becomes like an art, more like a real framework that you can study. And that's what happened in many works, that they try to analyze this, let's say, analytically. They try to introduce analytical methods, and it becomes like really, really complicated, and nobody really go that far. We saw that a lot during the pandemic, for example, with the meta population models, that then it was like, it became like you cannot even compare the model that was published in Science with the model that was published in Nature. They both start from the same assumptions, but the model became so complex that then the results you cannot even compare. So that's very problematic. And that is the norm, what I say, in complex systems, in ecological systems. The norm is that the equations will change over time. You get invasions, you get new technologies, you get new policies. So you need to have a framework where that is, you can user-friendly introduce it, not making it more and more complicated. So that's why in maybe the 70s, there was this new idea to model ecosystems by means of links. So we define an interaction. I am eaten by, and then I put an arrow that says, okay, the tail of the arrow says I'm eaten by, and the head of the arrow says I am eating what is on my tail. So then you can make a graph and describe who is eating who. That's the typical food web description. And it's very, very useful. Or you can also introduce another type of interaction like mutualism or parasitism or whatever sort of interaction you want to introduce. You can make a graph for this. The problem is that the arrow means one interaction. So in situations where context determine the interaction, then you might need more than one arrow. So you might have to introduce red arrows and blue arrows, let's say, which is what what's the name, the hypergraphs or multi-layered networks do. They introduce arrows of multiple colors, but then it becomes it becomes complicated to say what is the relation between red and blue arrows, because the language of graphs is meant to connect vertex nodes with one sort of vertex only. So then you can use numerical vertexes as well, label them by a number, which explains, okay, the extent at which something happens. But what can you do with that? Still, it still falls short, because there is no way to modify or to properly know how to modify that number from first principle. You need to start cooking the model. Okay, we will put these numbers and we will regulate the links, the numbers on the vertices in specific ways depending on the model. And again, it becomes a decision of the modeler to say, this is going to be the way in which I do my model. There is not a first principle way to decide that. And that's what is happening a lot. I will say, I'm open to change my mind. But what I have seen in models lately, since this idea of multi-layered networks, and I've seen also criticisms, that they really recognize, they assume that they don't have a way to build them. They just have to choose, use data, fit, and this and that. So the theory starts becoming shaky because it doesn't come from the proper first principles. So it's more like an art to build the right model. And again, this is the norm in complex systems. We do have contextuality all the time. So the idea of assuming an ontology of interactions is already shaky, in my opinion. I will say that there are maybe actions that one thing that does to its environment, and then interactions are more like mechanisms in which these actions couple, and we call these things interactions, but they are not really interactions. It's that we give them the name. Well, I may be going a little bit too far in what is the ontology of ecology here, but it's just the way to explain this idea, and we can discuss. And the last way to represent complex systems is agent-based modeling, which is very interesting because you can have lots of rules telling you exactly what each element in the system is going to do, maybe species, maybe resources, how the river is going to flow, how much sunlight do you get. You can also introduce policies. You can introduce, you can be God, play God with agent-based models. And that's really cool because you can simulate systems to a very detailed extent. The problem is that I haven't seen, you can show me if you have, but I haven't seen analytic methods to study complex system concepts, which are model independent. I've seen models of what is to cooperate, for example, in an agent-based model, a specific agent-based model, but I haven't seen like, this is cooperation for an agent-based model system, whatever it is about. There are no definitions of complex systemic concepts such as emergent, self-organization, or as I said, cooperation, etc. Like we have to create the definitions of these concepts that are model dependent. So the framework is not building up the ontology of complex systems concepts from the basis of the language in which we create the models. So they are very ad hoc in the end. You can do lots of simulations, do lots of analysis, but then you change the model, change 3 hypotheses or 2 hypotheses of your model, and then you get a completely different reality. So it's kind of hard to compare the results of different modeling approaches or different modeling hypotheses in agent-based models, because it all depends on the initial conditions of your model, on how do you Monte Carlo your model. Monte Carlo is, by the way, for those that don't know, Monte Carlo is a way to do a statistical modeling of a particular model. You run simulations exploring the space of possible conditions, and that's what is the idea of Monte Carlo simulation, exploring the space of possible conditions. So agent-based modeling is great modeling tool, but not so great for conceptual understanding. which is the real challenge in my opinion, or in the opinion of the literature, in complex systems. So we really don't, our challenge is at the conceptual level, not so much at the modeling level. We do have powerful computers and we have languages to represent complex systems, but now we need to build up concepts on top of that. So I will make a little summary here. So from a simulation point of view, we can really deal with several concepts, doing simulations and then definitions of how out of these simulations we can define concepts. That's totally okay. But then from a conceptual point of view, that means regardless of the initial conditions of your simulation and regardless of the time series, you would like to relate the language of your model, the description of your system, with some conceptual definitions. So this is a quick review. We could discuss it. So what I will do now is to go to another way to represent systems, which is not even that different, but all these notions become a little bit more clear. And that's why I think it's worth researching or learning or trying at least. So it's very simple. I changed this morning because I wanted to go straight to the point. But if we look at ecological, interactions as chemical reactions, it's very simple to look at. So, for example, amensalism, you get one of the species doesn't change, but the other gets depleted, the other gets negatively affected. So you say S1 plus S2, S1. Antagonism, S1 plus S2 is 2S1. So that means, for example, depredation, S1 it's S2 and can reproduce. Mutualism, both of them get benefited by it. Commensalism, it's one. The second one will be benefited by the presence of S1, but S1 doesn't change. And then competition, you can say S1 plus S2, S1, and S1 plus S2, S2. So they both will die or have a chance to die in the presence of the other. So the last one, competition, is interesting because it shows that the interaction requires two chemical reactions, not just one. Of course, these other four ecological interactions have a very simplified model. We are just representing the interaction by one reaction only. It's a very simple way to represent the interaction, but it's illustrative at least. But competition you cannot represent by just one reaction. You need at least two. And the point is that interactions might be represented as collections of reactions. That's the deep point that I want to mention or stress here. So let's do a slightly refined example. A system with two species, cyanobacteria and stentor, such that S2 feeds from S1, and S1 needs an inflow, something that comes from the environment, inflow like light to reproduce. So let's assume this very little system. What will be the reaction network? First reaction says the environment gives me light. Nothing, the empty set is the environment, gives me light. The second reaction, light plus cyanobacteria gives 2 cyanobacteria. Third reaction, cyanobacteria plus stentor gives 2 stentor. The fourth reaction is the light might also leave the system. The fifth reaction is that the cyanobacteria might also die and the stentor might also die. So this is a very, very simplistic description. And clearly, as I said, this SL, S1, S2 could be molecular species, could be bacteria, could be money, could be anything that influences another thing. It could be a human, or it could be basically anything. And the dynamical systems claim, because of course this we can turn into equations. As for those that know chemistry, we just simply have to, for example, apply the mass action kinetics, and we will obtain a system of differential equations that describes this system. Or we can do another stochastic modeling, or apply, I don't know, maybe this kinetics with maximal, what's the name of this? Mass action kinetics, and then this oh, I forgot, but there are other kinetics that don't allow for infinite reproduction, so they reach a sort of plateau. Saturated dynamics. But in dynamical systems, regardless of the kinetics we define, we always have that the realization of the states that the system will reach will depend on the initial state and the kinetic law in place. So we define a kinetic law, let's say mass action kinetics, and we define some initial condition, and we run the simulation or solve the equation if we can, and we will obtain the full dynamics. That's the paradigm of understanding the system. Then we can impose some sort of optimization paradigm to facilitate the solution of the problem, and then study the properties of the solution, for example, or that kind of thing, which will be the way in which we study this thing. That's the paradigm in which we study these problems. But that complexifies the analysis when the system grows large. So chemical organization theory has developed a computationally tractable framework to study, instead of the states that the system can reach, it study what parts of this system can self-sustain, can sustain in the long run through self-maintenance. That's the trick. What can sustain, it's actually what can self-sustain. And we don't need to calculate the dynamics. We just need to solve a linear programming problem, a matrix problem. So that's the trick. And now I will introduce a little spoiler. So because then I will introduce the theory. But the spoiler is that the chemical organizations are the parts of the reaction network that can operate in a self-maintaining, let's say, sustainable way. In this case, the light, cyanobacteria, and stentor. The three subsets of the system are organizations. But there is another subset, which is, for example, S1, S2, which is cyanobacteria and stentor. Together, they cannot survive. They cannot self-sustain because they need light. So there is a subset here. Actually, if you think of 3 species, you get 8 possible subsets. And out of the 8 possible subsets, only 3 of them can self-maintain. Only 3 of them, those 3, will be candidates to reach stability in the long run. And we don't need to calculate any equation. We know that any stable state will be either light alone, light and cyanobacteria, or the 3 things together. But light and stentor will not be a possible final state, a possible stable state. And neither light and neither cyanobacteria and stentor. And actually, we see the blue arrows that go up show what can happen if the system is perturbed. I will explain that, the perturbations, later. And the red arrows show the perturbations that are destructive to the system, and how the system can go to different states depending on the perturbations we do to it. So the idea now is, instead of studying the dynamics of a system to understand its long run stability, we will go straight to what can be stable in the first place, and then look at how this what can be stable change when we perturb structurally, and structurally I will explain in a second, when we perturb structurally the system. And now I explain the little structural perturbation. So we got again the light, cyanobacteria, and stentor, and let's say that a new species, S3, arrives because there was a mutation. So that, let's say it's a mutation of each of any of the 2, cyanobacteria or stentor, such that S3, it's light, but doesn't really help with it. It just destroys the light, and also eats the stentor. So it's in competition. Now we will say that it's in competition with the cyanobacteria because it's eating the stentor. And we say also that it's eating the light, so it's damaging the cyanobacteria as well. So It's eating the stentor, so it's a predator of the stentor, and it's in competition with the cyanobacteria, both for the light and for the stentor. So I don't remember exactly what's the interplay here. Let me go back. So S1 is the one eating light to reproduce. So then this one is competing with the cyanobacteria and is depredating the stentor. So the thing is that when this new arrival, new species come into play, the structure of what was stable, what was possibly stable in our dynamics, LS1 and LS2, will change to a new structure. And instead of calculating the dynamics of the system and then the new system, we look at the landscape of stability, and we look at the deformations or the evolution of the landscape of stability under different structural perturbations. So the question, so the question changes focus. It's not solving the dynamics of the system, it's looking at what can possibly remain as a stable set. So now I will introduce, if there are questions at this point, I'm happy to answer. If not, I continue now with the theory.
I have a question, actually.
Yeah.
So do you have to specify that the two species are competing with each other, as opposed to if they're both having this like plus, I don't know, like predation interaction on a resource? There's kind of like emergent competition there, right? Because they're both potentially depleting that resource. Sorry,
can you say that again?
Yeah, so do you need to specify that there is competition, as in that they're having two species are having negative effects on each other because they're competing for the same resource? Or could that emerge just because?
Emerge.
Okay,
I
so
mean,
you don't need to put a rule for competition?
No, there might be many ways for competing. So there is not one rule for competition. Different topologies will imply competition. You see what I mean? So we actually I'm eager to do an article about how can different structures mean what in ecology it's tend to be attributed to one kind of interaction, and say, okay, this is there are many ways in which this can happen. So yeah, I don't know if that it's on that direction, your question.
Yeah, I was just wondering about the idea of which kind of rules you actually need to specify in your system. So yes, thank you.
Okay, yeah, well, good.
I will comment, Tomás.
Yep.
Just so people, at least just to make sure that people in my lab is following. So these different boxes are different states of the system. So you just kind of, if you can comment on that, Tomás.
Yeah. Okay. So remember that the system has. Let's look at the small 3-box case, the smallest one, LS1 and LS1S2. So we have 3 species: light, cyanobacteria S1, and stentor S2. So the box the box means that only L is present in the system. So that will be the case where S1 and S2 got extinct or haven't yet arrived. They don't exist yet, maybe. Or they existed, but they died. So only light is present. If you think in the terms of the phase space of your dynamics, that will be the axis where light has a value and the other 2 axes have no value. So it's a one-dimensional part of the phase space. Then LS1 correspond to the states of the system, any state of the system where you have both light and cyanobacteria. So that's like a plane. We can see it like a plane in the 3-dimensional phase space. The phase space in this case has 3 dimensions: the population of light, the population of S1, and the population of S2. So these are actually, these boxes are subspaces of the phase space and each box represents, okay, I only have positive values on this axis, and on the other axis, I have 0. I have nothing. The species got depleted or hasn't yet arrived to the system. So that's the thing, that when we introduce a new species, in the second case, our phase space actually changes its dimension from 3 to 4. And when there is such a change in the phase space, it also changes the landscape of what can possibly be stable. Where in the phase space, in which subspaces of the phase space you will find the stable dynamics. So will that be a...
Yeah, perfect. Yeah. And also, okay. I always like to kind of bring people up to speed. I just wanted to say that Tomás is a physicist and then got a PhD in also more quantitative stuff. So he's not an ecologist. He's more in the mathy side of things, which is great. I'm saying that because in the room that you don't see everyone there are more applied math. There you go. There are more applied math than ecologists. So that's good, because in that way you don't feel lonely in terms of not having the language, the ecological words. And then the ecologists will need to kind of get up to speed.
Yes, I know.
In terms of what we're talking about more mathematically. But it's all good. It's great. So and also mention that those arrows going down that are red, for example, I'm interpreting those as losing a species. That's why you were saying that there were perturbations. So from everyone present in the third box top in the first diagram, you have the 3 species present, and then the first arrow, red arrow, goes down. You are losing species 2. Yes. And then going down, you species, and then the blue are kind of more maybe invasions or.
Yeah, I will give a very detailed description of these dynamics in a bit. So
great. Sounds
so good. If you're still confused, wait, because it's coming in more and more strict detail.
And also just to finish my
thank you.
Finish my intervention is I'm bringing Tomás to the lab meeting because he's having this very new, interesting way to study networks, the dynamics of networks, with a different set of mathematical tools. That's the reason.
Yeah, and also, I'm sorry that I didn't introduce myself, because I come from an interdisciplinary background, studied physics first, then math, and then computer science. So I have the three degrees, I will say, and yes, I speak a very clumsy ecology language. So when I say ecosystem or community, I might mean the same thing, and I know that for ecologists this is like a sin. So I'm a sinful ecologist, let's say, but I try to bring the mathematical framework for doing models. So I apologize. I should have said this before, for my ignorant language. And this is what I'm looking for. I'm looking for more interactions and more connections with ecologists to have the chance to learn from each other. So okay, keep going with the theory now.
Actually, before we move on, sorry.
Moment. There is some feedback loop.
I think that Casey, there you go.
Sorry about that. It's me being an idiot. So actually, before we move on, could you go back to that slide that had the 2 diagrams on it? So we were having a little bit of side conversation about, on the diagram on the right, why is L S1 S3 not also a end state? And so I guess maybe I should wait and let you continue with your presentation, because I'm sure you're going to explain how these end states are determined. But just from inspection of the equations that were given, it looks like both S1 and S3 could survive as long as light was existing without S2. So I was hoping if you could explain maybe the methodology behind how these end states are determined, and that might clarify some of these things. And that might also just be like the rest of your talk. So sorry if I jump at it.
Yeah. I'm not sure if I have an immediate. Let me see. I think it's simple enough, but the problem is that we will need a little bit of whiteboard. So LS3, you got this in mind, right? The R1 to R6. Okay, we got to keep everything R1 to R6 and then R7 also in mind. And the question is why LS3 is a potentially stable state?
No, why is LS1 S3 not also a stable state?
Why is not? Yeah, it could be. Maybe I'm missing this box. LS1 S3 L. As long as there is enough light, this should survive, you say?
That's if I'm understanding.
Yeah, I think you're right. I think it might be possible that LS1 S3.
But I guess just in general.
Yeah. No, yeah. Because you get light LS1 to S1. Yeah. No, that works. Yes.
Oh, perfect. So I guess just, are you gonna talk about how these end states are determined?
Yes.
Okay.
Yes. This is an illustration more pictorial than precise. So okay. I'm now going to introduce the reasons why all these boxes can or not be stable. Excellent. So thanks for the remark. Yeah, okay. Let's go to the general description. Yeah, we will assume N species and K reactions. And then the change of focus here is that instead of studying the dynamics, we will study the sub-networks of the reaction network. So first thing to understand is that when you choose a subset of a species, you activate a subset of the reactions. So the full network, MR, the N species and the K reactions, is like the potential universe of possibilities. And then Rx is a system of interest. Okay, so I will introduce a few notions here. It's just to go with it. Let's think of this one reaction. A plus B goes to C. So your universe of possibilities is ABC. We call the support of the reaction what it is needed for it to trigger, and the products of the reaction, what it is produced by the reaction. So we need to introduce these notions. Many other languages have them as well, like in Petri nets, if anybody knows them. Now, if X is only A, then the reaction set is empty because you cannot trigger any reaction having only A. And interestingly, what it is produced by the reactions is already part of the system because it produced nothing, and the empty set is always part of any other set. So in this sense, we can say that A itself is a closed set because it doesn't produce anything new by the reactions that it triggers. Differently, you get, if you start from AB, then your reaction set will be R, and then the products of the reaction are not part of the set that we are taking into consideration. So then AB is not closed, but ABC is closed because the products are already contained in the set. So if we think that this brings the idea of thinking that certain parts of the network are closed because whatever it's produced by the reactions in it, it's already contained in it. And that's not always the case, only for the full reaction, only for the full network. You can have many closed reaction networks within the larger one. And that's a very interesting aspect of the analysis. So we define then the, this is I'm sorry, this should be if products of Rx are containing X, then the X is closed. This other condition, products of Rx subset of the support of Rx, is called semi-self-maintaining, which means that everything that is consumed can also be produced. Oh no, it should be the inequality the other way around. Oh, that's a very clumsy mistake. So how can I fix it with this remote control? More annotate, may a annotate? No chance to annotate. So here it should be X only, like it's here. So if this happened, but Rx here, so for all reactions, if the union of the products of all reactions are part of the set, then the set is closed. If you got the imagination, you can feel it. So it's not support, it's only X. And the interesting thing is that the closed sets are already much less than the subsets, that we know that these are 2 to the power of n. If we got n species, we got 2 to the power of n subsets. And the closed sets, generally, these have been studied for different topologies, different networks. It's normally like square root, the square of n, more or less. It can be 1.5, the power to 1 or power to 1.5 or something like, but it's a polynomial, generally polynomial. And there are many other reasons by which we can reduce the set of closed sets. So these are already many, many less than the set of possible subsets. And now we introduce the notion of process. So, and this is a very crucial notion for the model, because we got a topology, but we can also operate this topology, operate the way in which things are produced. So a process is a specification of how reactions happen. And we set up a time interval, like an abstract time interval. We don't really care much about it because of linearity. I think there will be a chance to explain this later, but we don't care much about this, about the time interval. We only say, okay, we assume a span of time, and we say we're going to have this much of reactions happening. So the process implies a collective transformation. Let's think of this system, because it's very easy to think in this system. A, B, C, and 3 reactions. A plus B goes to 2C, B plus C goes to 2A, and A plus C goes to 2B. Process R1 consumes 1A, 1B, 0C, and produces 0A, 0B, 2C. Process R1, R2, meaning 1 time R1, 1 time R2, like a sequence, consumes 1A, 2B, 1C, and produces 2A, 0B, 2C. And then process R1, R2, R3, so 3 reactions at the same rate, specifically, or apply 1 time, if we think in discrete dynamics, we consume 2A, 2B, 2C, and we produce 2A, 2B, 2C. So this process is called self-maintaining, because it produces the same or more than what we consume. And this is, there is an extra condition that we need to demand theoretically, that all the reactions that can possibly happen must happen. So this is a little bit of a technical detail that we can also discuss later. I will not go into super technical stuff, but just introduce the general idea. So the idea is that there are processes that self-produce the system. And then this is when the notion of organization comes in. An organization is a closed and self-maintaining set of the reaction network. And this is where the theorems come. So stationary states of a reaction network will correspond to a set of organizations. No, if it's a fixed point, it will be one organization. If it's a periodic orbit, it might correspond to 2, 3, 4 organizations, which are generally quite related. Heteroclinic trajectories also correspond to set of organizations, limit cycles as well. So this has been deeply studied for mass action kinetics and also for the reaction diffusion systems as well. So the solutions of pretty much every differential equation model of a reaction network, for those, we will find that the stationary states, those things that we conceive mathematically as stable, will be mapped to organizations. So that's the idea, that organizations are a sort of landscape of what can possibly be stable, but without solving the equation, at the cost of not knowing the specific state. We do not know the specific state, which is in the fixed point, or which is in the, or what is the limit cycle. We don't know exactly the values of it, but we know it's in this part of the phase space. And I think that for ecology or for chemistry, this is quite interesting, because in principle, we don't need to know how many foxes we will have, if we have 100 or 105, and how many rabbits if we have 10 or 12 or 100. We just need to know that we have foxes and we have rabbits. Maybe later, once we know that, we can go more precise and then run simulations for specific cases in those for those pieces of the phase space, and learn more about the quantitative dynamics. But in principle, this gives us a qualitative landscape of what can be stable. So following the analysis of the people there, yes, LS3 will be closed, and I think it was closed, yeah, and it was also self-maintaining. And this is the typical picture of how this is studied. We got the landscape of organizations, and then we look at what changes in the phase space will drive to changes in the stable state. And we got trajectories going up, trajectories going down, or sidewards too, and then we can look at the quantitative concentration, as I said here, in simulations. So the idea is that traditional dynamical system program consists of understanding the conditions under which each transition becomes realized, based on attraction, stability, etc. But for us, the idea that we are pursuing, is the idea that we shall instead try to look for structural features that make certain organizations more resilient than others. So that will be found more frequently in a dynamics that has permanent perturbations. So the hypothesis of our project actually is that dynamical evolution will ensure the discovery of resilient structures that first of all are able to self-produce, and also that implement behavioral mechanisms in the stable emergent whole that tend to preserve its self-productive capacity and potentially other capacities in the presence of perturbations. So we look at now the landscape of organizations. This is an abstract picture, and we will say, okay, this is non-resilient. These are already organizations. So these are already candidates to be stable. But then some of them will be more resilient than others. So then the dynamics, the evolution of our complex system will tend to visit more often organizations that are more resilient, or maybe collections of organizations that as a whole are resilient. This is a novel hypothesis we don't formalize yet. So how does that look? Then we will see that when perturbations go from non-resilient or partially resilient to resilient, then they will tend to remain in the resilient state. But that's also pictorial. Don't ask me about what this arrow, that arrow, sorry, it's just pictorial. It's to show that the idea that certain structures will be like attractors, but in a stochastic sense, that many perturbations will tend to drive to them. So we have a structural random walk framework implemented, and it's very new. We just submitted it to Artificial Life, the conference, and we will be presenting it in a couple of months. So we don't have yet the article ready, and we are also testing only with random reaction networks, because we would like to have, and that's the reason why I contacted Fernanda a few months ago. It's because I'm looking for reaction networks that will represent ecological systems, to see how these methods look. And we also have kind of like frameworks or approaches to study the complexity stability debate, or that sort of thing. So the idea is that we define a structural random walk as a dynamical evolution over periods of time. As I said, the time for us is not very relevant at this moment. We can go and make more details about that. And then we have perturbations at each period. By perturbation, we mean that we can change the state of the system, depending if we're running a simulation, kinetic parameters, or add new species or reactions. In this case, for this seminar, we will only look at changes in the structure, so adding or eliminating species. So the idea is that we are in a specific organization here in the middle. They have a subscripts because they are, this is a picture from the article, and we separate organizations by their size, H, how many species the organization has, and L is the index in the horizontal axis. So we are an organization HL, let's say, and let's say we add a species Y1. So we take O union OHL union Y1, and then we take the closure. We obtain the closure. That means recursively add the products of the reactions. We recursively add the products of the reactions. So we get new species by the products. These products will activate new reactions. This reaction will give new products that will activate new reactions, and so on and so forth, until recursively we will converge to a new closed set. So maybe I will give more details of those operations in the next week. So for now, that gives us a new closed set, and that closed set might be self-maintaining, as in case Y1, or might not be self-maintaining. So we reach the closure of OHL union Y2. This is closed, but it's not self-maintaining. So we have to see to which organization will collapse, because if you reach a closed set that is not self-maintaining, that means that something cannot be self-maintained. That something that cannot be self-maintained will deplete, which in turn will modify the set of possible reactions. If that thing is again non-self-maintaining, it will also collapse to a smaller and smaller and smaller, until at some point the system will collapse to something that is closed and self-maintaining. So, and we assume that in our dynamics, we look for those organizations that are closer to it, to the one that is to the one that is closed. This one here, we look to the smallest, to the least further away organizations to this closed set, and we give them equal probability to collapse. This is our simple dynamics. We are not running dynamical simulations. We just do a random walk over the space of organizations and closed sets. And also we can have a perturbation that eliminates something. Let's say there was a heat wave that eliminated a given some species, and then again we compute the closure of the system without this species, because some reactions will be eliminated, and then we have to check what can be applied, or what can survive, and we go again back to some organizations that can be in the bottom, or might be stable in case this is already an organization. I'm not sure if this is clear to you. I hope it is, but it's a simple random walk over the possible structures that can be stable in the reaction network, and we need to compute the closure and check whether or not that closed set is self-maintaining, so it is an organization. That's the full idea. And then what we see, this is a picture only to finish. I'm finishing here. What we see, which is very interesting, is this is a plot of the size of the set, not the structure, but the size of the set before the perturbation, and this is the size of the set after convergence, the closure, and then collapse to the self-maintaining set. And we start from this is a random reaction network of maybe 40 reactions and 70 species or something. We work only with random reaction networks because we are testing our methods. So this is a typical case. We took many, and this is the typical. It's not it's picked up specifically for it. It's what happens most of the time. So we start from a small system, and we start perturbing it, adding and adding and adding more species. So it goes to larger and larger organizations. And at some point, it goes to a very large one, which, as you can see, then it remains stable. So it resists some perturbations, but then there is a big drop. So some perturbation made it to destroy a big part of it, but then again went nearby. It didn't change so much, and it tends to stabilize, as you can see. in some organization, which is kind of middle size with respect to the reaction network. So that means that there is a resilient organization. There is one that ends up being the attractor. In the space of possible stable states, there are some stable states that are attractors. You see, it's like a meta attractor. And the interesting thing is that in this plot, you can see the dynamics of exploration on the upper side and of regression or kind of collapse in the bottom side, because the diagonal size is preserved by the transition. So we have tried many of these plots, and it always looks like this sort of spiral dynamics. And if we try with even larger networks, we see this, and then it remains a little bit, and then it grows again and goes even bigger. And then we discover like more and more resilient structures, the more complex the reaction network is. But this is all in testing for the moment. So yeah, I think I missed some interesting pictures, but I can show them on next week. So the idea is that a theoretical algorithmic approach to study the emergence of resilient reaction networks. Most of the theoretical developments and computational results are to be explained still on next week. And we also have many advances that we are working on. And this is the team of people working on it. So without them, this could not be possible. So thank you.
Great. So let's start with some questions, and even like people that I don't know in the Zoom can ask questions or in the room. I think that you have your students there as well, Tomas,
Yeah.
right? Yeah. So anybody can ask.
Okay, am I audible? Hello.
Hello.
Yeah, can you hear me?
Yep.
It was very nice talk, amazing concept to hear about. And I just have one, I'm curious to know whether this approach can be applied for the predictability of critical transitions too, or maybe you're working in the similar direction or something like that. Because can it be related to predictability of critical transitions in network?
I think it by critical transition, what do you mean?
By critical transition, for example, a sudden shift in the state of the system, like if there, for example, if I have a system full of species X and suddenly a very sudden jump and there is extinction of all the species, something like that.
Yeah. It can definitely. That's. I mean, it depends on at the level you want to think of perturbation, because at the moment for today, actually, this is a critical transition here.
Okay.
This one is a critical transition because you got a system of 40 something species, and then you get something of 15 species. So this perturbation activates the critical transition.
Okay.
In the plot.
Okay.
And this is the opposite. This is a critical constructibility. This is like a meta. What is it called? This a meta evolution? No, when bacteria that process oxygen emerge. What's this like? There are some stages in evolution where you see like explosion of biodiversity as well. You know that?
I think it's called a meta transition in evolution.
Meta transition in evolution. Thanks, Matthew. Yes. So you get also meta transitions in evolution and also critical transitions in extinction. So you can see the two things. Yes. Sorry, Sophie. Yeah.
Yeah, thank you. And how do you decide which reaction is occurring? Like, is it probabilistic?
In the dynamics here?
Yeah.
We started this thing here. It's a very basic model of probability. We only add we throw toss a coin, 1, 2, or 3 species will be added or eliminated. That's all. It's a Poisson, let's say, process. So we choose how many species will be added or eliminated, and then for that number we choose randomly which of those will be added or eliminated. And we are also thinking of because this is just I mean, technically I could share with you the article, because this is a probability distribution that we have to define. What is the probability of perturbating the system? And I think that maybe a power law will make a much better realistic job at describing what perturbations happen, because we know that they tend to follow a much not so homogeneous distribution in terms of which species are perturbating, and also the number of species in the perturbation should have a different law. So some perturbations will be much more often than others. That's the point. And that will change the dynamics. That certainly will change this plot, certainly. But the framework is going to be intact. So then that's the interesting point, I think, of the talk, is the framework more than the specific results. And with you, with the collaboration with the group, we can make realistic assumptions about that. I will be really interested on checking on that.
Yeah, and I also just, I'm not sure if this question makes sense, but like you are giving a perturbation in the state variable, which I see. Is it possible, like, can this framework be followed if I give a perturbation in the parameter of the system rather than?
Yeah, but instead the dynamics here, that's the thing, that the black arrow here, because this is a simplified, we are making a qualitative dynamics here. So we only have a set, and then we run a dynamics that means compute the closure, check self-maintenance. If it is self-maintaining, and in this case, you stay there. And if not, then try to go stochastically with equal probability to the most likely next organization, which is the closest one. But that's a specific dynamics we are using exactly to avoid states and parameters. But instead, we can compute. We are running, actually, we have another code now running or testing, that now we make a perturbation that is not necessarily adding a new species, but maybe change the kinetics parameter, for example, and then we run the same. We do the same algorithm, but instead of adding a species, we just change the kinetic parameter, and we run the kinetics for, I don't know, 1,000 steps or 100 steps, and we see where it goes, and then we recalculate the organization, and then so yeah, I mean, the framework is completely flexible to that. It's just that certain routines within the algorithm will have to be changed from qualitative to quantitative dynamics. And as I said, we can work with mass action kinetics, saturated dynamics, or maybe metapopulation models. All this can be embedded in the same framework. And conceptually speaking, nothing changes. So that's why I think this is a different layer. I mean, that's why I claim that this framework allows for conceptual understanding, because then the other things are implementations of the dynamics, but the concepts remain untouched by different models or by different dynamic decisions, which that's not always the case for agent-based models or other frameworks. So that's the power here, that the concepts are like independent of the specific implementation. Yeah.
Yeah, thank you so much.
Yeah, thanks. Oh, you're muted, Fer.
Yeah, so I think because I also want to kind of go down to be in person, like to close the meeting with my group. So I will probably wrap it up here, but we have you next week. We will make sure that the room works for the hybrid options. So, and thank you very much, Tomas. It was great. I think that we have a lot to discuss with my group in terms of collaborations with you and your collaborators.
Share networks with me.
Right, we have a ton of networks we can share with you.
We can test them. I will show you next week the software. I spoke with the programmer, with Pedro, and we will prepare a few beautiful plots for you for next week, and also a bit of theory.
Okay.
Yeah.
Wonderful. Yeah, so we're looking forward to that. And
Okay.
I will stop the recording.
Thank you.
Yeah.